Imagine trying to teach a massive cluster of GPUs to watch a simple video of a bouncing ball. But halfway through the video, the system literally runs out of memory because it forgot how to process time. And, when it finally generates the next frame, the ball just floats away because the model never actually understood gravity.
Yeah, it breaks completely.
Right. And that is the exact mathematical wall the AI industry is slamming into today. Welcome to AI Paper Slop. Today, we are tearing down a foundational new paper from Tencent U2 Lab and their collaborating universities called NMM Roadmap toward native multimodal modeling.
And if you are an ML engineer, you already know the old paradigm of stitching together separate frozen vision and text encoders is, well, it's dead.
Completely dead. The entire industry is aggressively shifting toward early fusion, native multimodal modeling, or NMM.
Right, which basically means building multi-to-multi architectures where your text, audio, image, and video all live in a single shared transformer space right from layer one.
Exactly. And for the next few minutes, we are unpacking the industrial-grade blueprints for this transition. We're going to cover exactly how your training recipes must change, specifically, the mechanics of differential learning rates and on-policy distillation.
Not to mention the deployment tactics required to actually serve these massive architectures.
Oh, absolutely. Like adaptive perception.
Yeah.
This is your hype-free technical briefing on building true-world models. So let's just get into it.
Yeah, to really engineer these born native models, we have to understand the evolutionary path the paper defines. I mean, the industry hasn't just randomly decided to throw everything into one big transformer.
Right. It's a calculated response to some pretty severe information bottlenecks.
Exactly. And the paper categorizes this architectural evolution into three distinct phases. You've got late fusion, mid-fusion, and then the current frontier, early fusion.
Okay, let's unpack this taxonomy. Because visualizing the architecture really makes the underlying mathematical realities click. Let's start with late fusion. This is the old, connect and generator way. You take completely independent decoupled encoders, say a vision transformer trained on images and an acoustic model trained on waveforms. You keep your massive language backbone completely frozen, and you just graft a simple projection layer in between them.
Models like LV do exactly this.
Yeah, LV. So if I had to use an analogy, late fusion is it's like a United Nations assembly. Every modality is speaking its own native biological language, and they're relying on these sluggish, highly lossy earpiece translators to communicate with the LLM.
It functionally works, but it's very disconnected.
Exactly. Then the industry moved to mid-fusion. Here, the model gains real cross-modal insight, but it still maintains explicit modality-aware boundaries inside the network. So sticking with the analogy, mid-fusion is a team of bilingual speakers. They collaborate much faster, but mentally they are still looking up words in separate dictionaries.
Which is a huge bottleneck.
It is. And then we reach early fusion, the holy grail, the born native paradigm. This is a newly invented universal telepathic language where concepts just exist natively. All modalities, the pixels, the waveforms, the discrete text tokens, they're all processed by a unified native transformer in a single shared embedding space.
What's fascinating here is how accurately that telepathy analogy maps directly to the mathematical reality of the transformer's attention mechanism. Erasing those explicit modality-aware boundaries isn't just an aesthetic architectural choice.
No, it's necessary.
It is strictly necessary for true cross-modal reasoning. Let's look at late fusion again. In that setup, the large language model is effectively blind to the raw sensory data.
Because it only sees what the projection layer gives it.
Exactly. It only sees a highly compressed, quantized representation that the projection layer forces through. You're permanently losing high-frequency visual or audio details before the LLM even does a single calculation. Yeah, so by moving to early fusion, you eliminate that structural bottleneck entirely. When the query key and value matrices in the attention heads do their matrix multiplications, they are treating a 16 by 16 pixel patch, embedding exactly the same way they treat a subword text token.
It's all just data to them.
Right. It is a single continuous mathematical space where a word and a pixel can directly compute their semantic relevance to one another.
Which naturally leads to the biggest engineering headache. If the network sees everything as the same telepathic soup, how does it know whether to generate a word, a pixel, or like an audio waveform on the way out?
Yeah, that is the million-dollar question.
Yeah.
Because comprehending a video is one thing, but generating one from scratch exposes massive new bottlenecks.
Right. And the paper tackles this by laying out an input-output duality framework. It starts with multi-to-text, or M2T. That's basic comprehension multimodal input discrete text output. Then you get multi-to-target, M2G, which is scenario-oriented generation, like text to video.
And finally, symmetric multi-to-multi, M2M, where it's continuous multimodal streaming in both directions.
But the generation side of this, especially video, is just an absolute nightmare for transformers.
And it really is a nightmare.
Yeah.
And the paper makes a point of breaking down exactly why it's so difficult. The first major hurdle in video generation is physics understanding. And it's a fundamental limitation of how transformers learn.
Right, because an LLM learns statistical patterns, not Newton's laws.
Exactly.
It can generate a photorealistic image of a glass falling off a table perfectly because it has seen millions of static images of glasses. But when you ask it to generate the video of the glass shattering on the floor, it fails.
It doesn't actually have an internal physics engine. It's just guessing the next most probable pixel arrangement. Gravity simply doesn't exist in its latent space.
And trying to teach it those physics leads directly to the second massive hurdle, which is token explosion.
Yeah, moving from a static image to video, you aren't just adding data, You're adding a temporal dimension. You are creating a massive spatiotemporal grid.
So your sequence length goes entirely parabolic.
Precisely. And standard transformers have quadratic complexity in their attention mechanism. So if you double the number of tokens...
The compute required quadruples.
Right. Processing a 10-second video natively crushes the memory limits of even the largest GPU clusters.
And even if you solve the memory, you hit the third hurdle they mention, which is audio-visual alignment. Generating a video where the visual impact of an object like a hammer hitting a nail perfectly syncs with the generated acoustic waveform spike is incredibly fragile.
Because you are trying to align two fundamentally different frequencies of data in the exact same forward pass.
Which is why the industry is desperately searching for algorithmic breakthroughs to bypass these bottlenecks, particularly on the audio side where latency is so heavily scrutinized by end users.
Yeah, audio latency is brutal.
Here's where it gets really interesting, though. When the authors dive into solving these massive audio latency bottlenecks, they bring up Nemotron 3 Nano Omni. And, if you are an ML engineer, you have to geek out over the sheer elegance of this architecture.
It is brilliant.
To solve the high latency and compute cost of audio, Nemotron uses a 31 billion parameter Mamba 2 transformer hybrid mixture of experts, but it only activates 3 billion parameters per forward pass.
Right, because Mamba 2 is a state space model, which means it completely sidesteps the transformer's quadratic scaling problem.
Right, because state space models compress context into a hidden state rather than recomputing attention over every single previous token.
Exactly. Mamba 2 achieves O of n linear complexity. This is how you survive the token explosion. But Nemotron goes even further. It doesn't just process the tokens more efficiently, it aggressively filters them before they even reach the core processing layers.
Yes, the active pruning, this blew my mind. The underlying decoder dynamically predicts token durations and literally skips silent acoustic frames.
Yeah, if there's a pause in the user's speech, the model doesn't waste precious compute multiplying zeros.
It just throws the frame away. It prunes the sequence on the fly.
And that is a perfect example of what the authors call algorithmic architectural co-optimization. You simply cannot solve the real-time speech interaction problem just by throwing more H100s at a standard autoregressive transformer.
No, the latency budget for natural human conversation is what, about 200 to 300 milliseconds?
Right around there. Any longer, and the user feels a lag, and the conversation just breaks down. If you don't co-optimize the architecture leveraging linear scaling and dynamic filtering, you will never achieve the necessary system throughput.
Which brings us to a really painful topic for anyone who has ever tried to spin up a massive training run, the actual training recipes, because you can design the most elegant early fusion Mamba hybrid in the world, but it's completely useless if the loss diverges and the model explodes halfway through pre-training.
And this paper makes a really profound argument here. The fusion regime you choose, whether it's mid-fusion or early fusion, entirely dictates your training signature.
It is no longer just about stacking layers, it is delicate chemistry.
Let's examine mid-fusion training first. The paper states unequivocally that for mid-fusion architectures, strict differential learning rates are absolutely mandatory. You cannot use a uniform learning rate across the entire network.
Interesting.
For example, they point out that CogVLM applies exactly 1/10 of the base learning rate to its vision encoder when they finally unfreeze it.
Okay, and Moshi uses roughly a 7x gap between its temporal transformers and its depth transformers,
Yeah,
right?
they deliberately throttle the gradients flowing into specific components.
Wait, let me push back on that for a second. Why wouldn't a uniform learning rate just eventually settle? I know we're talking about billions of parameters in complex loss landscapes, but from a basic optimization standpoint, why does the encoder completely break down if it simply gets the exact same learning rate as the massive LLM backbone?
Well, if we connect this to the bigger picture of how these models are actually initialized, the underlying math becomes clear. Your LLM backbone is a massive, heavily stabilized structure. It has usually been pre-trained on trillions of text tokens. It sits in a very deep, very stable minimum in the loss landscape. To actually shift its weights and learn new multimodal behaviors, it requires a relatively high learning rate.
Makes sense.
But your vision encoder is often much smaller, or it's being exposed to gradients from a completely new joint multimodal distribution for the very first time. Its weights are fragile.
So if you hit that fragile encoder with the massive learning rate required to move the stubbornly stable LLM.
You blow out the encoder's weights, the gradients compound too aggressively, the weight updates overshoot the optimal minima, and mathematically your loss goes to nan, not a number, almost instantly.
Wow, the whole representation just collapses.
Almost instantly. Conversely, if you drop the global learning rate low enough to protect the vision encoder, the LLM backbone stops learning altogether. It barely updates.
So training these systems is no longer standard convex optimization. It is strict ecosystem management. You are balancing two fundamentally different biological systems in the same tank.
That's a great way to put it.
Okay, that makes perfect sense. The differential learning rate is the mid-fusion survival tactic, but what about early fusion? If everything, the text, the audio, the vision, is built into a single unified native transformer from layer 1, you can't exactly apply different learning rates to different modalities.
Right, because there are no explicit modality boundaries anymore.
Exactly.
And that introduces a completely different existential threat. For early fusion pre-training, the critical survival tactic is precise modality mixture scheduling. You are meticulously managing the ratio of text to images to audio in your training batches.
And if you fail to schedule that mixture perfectly,
You trigger a failure mode the literature refers to as Chameleon's warning.
Chameleon's warning. That sounds like an ominous sci-fi trope where the AI turns on its creators.
It really does. But mathematically, it describes a very real, very degenerate failure mode. Chameleon's warning highlights that if an early fusion model is exposed to an imbalanced mixture during training, usually heavily skewed toward text, it learns degenerate unconditional language priors.
Because text is so dense. A single paragraph contains immense, high-level semantic meaning compared to, like, an array of raw pixel values.
Precisely. Text is highly compressed human knowledge. Raw pixels are just noisy, continuous sensory data. So the unified transformer essentially gets lazy.
It takes the easy way out.
Yeah, it realizes it can minimize its loss function just by relying on its powerful text prediction capabilities, and it completely ignores the complex, high-dimensional visual or auditory evidence you are feeding it alongside the text.
It ruins the model's ability to actually generate or reason about non-text modalities.
Exactly.
It turns into a text snob. It just refuses to look at the pictures because reading the summary is easier. And this tension doesn't just happen in the pre-training phase, does it?
No, the paper notes that this exact same dynamic causes massive headaches when we move to the alignment phase, when we try to teach these models human preferences using reinforcement learning.
Right. Standard RL, like direct preference optimization or DPO, completely falls apart in early fusion. In mid-fusion, because you still have those modality boundaries, you can survive by decoupling the pathways. You can use things like MDPO, which explicitly conditions the preference loss directly on the image representation.
But early fusion RL suffers from this brutal phenomenon called the Seesaw effect.
Right, the Seesaw effect.
It is the absolute bane of multi-objective post-training. In a unified telepathic embedding space, everything is connected. So the gradients from different capabilities actively fight each other.
Wait, really? So improving one thing breaks another?
Yes. If you run a standard RL pipeline to improve the model's mathematical reasoning, its visual generation regresses. If you optimize it to write better Python code, its instruction following for audio degrades. The model constantly forgets one skill to learn another.
That's crazy.
Standard RL provides a reward that is just too sparse.
Right, because standard RL might just give the model a generic +1 reward at the very end of a sequence for a good answer. It doesn't tell the model exactly how it got there.
Exactly. The solution the paper points to is on-policy distillation, or OPD, and specifically multi-teacher OPD. Models like Mimo v2.5 use this extensively.
And to really ground this for the engineers listening, let's unpack how OPD stops the seesaw effect. Instead of just relying on sparse rewards, on-policy distillation uses a stop-gradient reverse KL log ratio.
Let's break that jargon down because the mechanism is vital. KL divergence, or Kullback-Leibler divergence, is a mathematical way of measuring how one probability distribution differs from another.
Right, so in this setup, you have your massive, highly capable teacher model and your smaller, early fusion student model. For every single token in a sequence, the teacher model generates a full probability distribution over the entire vocabulary.
It says, I am 80% sure the next word is the, 10% sure it's a, and so on.
And instead of just giving the student a +1 reward for guessing it, though, reverse KL divergence forces the student to perfectly match the precise shape of the teacher's entire probability distribution, position by position, token by token.
Exactly. It provides dense, per-token supervision. And the stop gradient part means you are only updating the student's weights, not the teacher's. The teacher acts as an immovable anchor.
So this massive influx of dense supervision stabilizes the RL phase.
It locks the weights in place so you don't get that seesaw regression. It forces the student to respect the complex multimodal distribution of the teacher without forgetting its prior capabilities.
So let's say we pull all of this off. We architect a beautiful early fusion M2M model. We perfectly manage our data mixture so we don't trigger Chameleon's warning, and we use on-policy distillation to align it without the seesaw effect. The final boss is deployment. We actually have to serve this massive behemoth to users in the real world.
And this is where the theoretical architecture slams headfirst into physical hardware limitations. The paper outlines the dual challenges of deployment: heterogeneity and scale.
Heterogeneity because you are asking a single inference engine to serve abstract, discrete text tokens alongside massive, high-dimensional, continuous video and audio signals.
Exactly. And scale, because flagship NMMs are rapidly moving toward the trillion parameter mark. Models like Kimi-Key 2.5 or Ming Flash Omni 2.0, they are a massive mixture of expert systems. Serving them at scale requires entirely new infrastructural paradigms.
The paper essentially declares that static offline generation is dead. If you are an engineer building for the future, the entire shift is toward real-time streaming and full duplex deployment. Metrics like time to first token, TTFT, and sustained interactive latency are the new primary optimization targets.
We are seeing early versions of this with systems like Moshi and FireEd Chat.
Right, the user speaks, and the AI needs to process the audio, think, and start speaking back instantly, while simultaneously listening to the stream to see if the user interrupts it. But here is the massive physical bottleneck: the KV cache.
Yes, the key value cache is the silent killer of multimodal deployment.
Let's unpack the mechanism of the KV cache for a second. When an autoregressive transformer generates text, it generates one token at a time. To generate the 100th token, it needs to look back at the previous 99.
And if it recomputed the math for all 99 previous tokens every single step, it would just grind to a halt.
So it caches the key and value vectors of the previous tokens in the GPU's VRAM. But with video inputs, at 30 frames a second, you are generating tens of thousands of tokens instantly.
Right. The VRAM required just to hold the KV cache for a short video completely exceeds the 80 gigabytes available on standard accelerators.
Your memory blows up before your compute does.
Which means you have to fundamentally change how the model perceives the stream. You cannot physically process and cache every pixel of every frame. The paper highlights the absolute necessity of adaptive perception.
Adaptive perception.
Yeah, this is the concept of selectively spending your compute and memory budget only on the highly informative regions of the input stream.
So what does this all mean in practice? The paper brings up a system called readapt, and the numbers here are staggering. Readapt actively eliminates over 90% of the visual tokens from a video stream.
Which sounds crazy, right?
It does. But by dropping 90% of the data, it expands the temporal horizon of the model by 16x. It dynamically figures out which patches of the video actually contain new semantic meaning like a person walking into the frame, and it just drops the redundant background pixels from the KV cache entirely.
It is an incredible optimization. But to implement it, System algorithm co-design is the absolute most critical frontier right now. You can no longer design a brilliant early fusion architecture in PyTorch, pat yourself on the back, and just throw it over the wall to the systems team to figure out how to serve it.
No, optimizing low-level CUDA kernels, managing sparse modality-aware KV caches, and figuring out expert routing for these massive trillion-parameter MOEs that has to be designed hand-in-hand with the mathematical architecture itself.
Exactly. If your attention kernel isn't built from the ground up at the silicon level to handle the highly sparse, dynamically pruned multimodal streams that something like readapt produces, your model is dead on arrival in a production environment.
It's all connected.
It really is. And this raises an important question, however, regarding how we as an industry are even tracking our progress toward these deployment goals. The paper delivers a very sharp critique of our current evaluation methods.
That our static benchmarks are entirely failing us.
Entirely. Right now, we measure a model's accuracy on an isolated frozen image. Or we ask it a multiple choice question about a static text prompt.
Which doesn't reflect reality.
No. These benchmarks do not measure sustained streaming latency. They do not measure temporal awareness across a 10-minute video where the model has to selectively prune its KD cache. And they certainly don't measure how gracefully a full duplex model handles streaming input or deals with a user interrupting it mid-sentence.
We're building these highly dynamic interactive agents, but we are still grading them with static, offline, accuracy-only scorecards.
It's a huge disconnect.
Which perfectly tees up the ultimate endgame this roadmap is pointing us toward. The industry is moving far, far beyond just adding multimodal chat to an LLM. We are tracking a direct structural evolution from those clunky, stitched-together late fusion models to mid-fusion hybrids with explicit boundaries, and finally, to born-native symmetric streaming intelligence.
Native world models.
Native world models, that is the destination. If you are building in this space, achieving this early fusion, M2M reality, is the defining technical challenge of the next few years. It's going to require rethinking everything from how we schedule our pre-training data mixtures to avoid Chameleon's warning, to how we use reverse KL divergence to stabilize alignment, to how we write our low-level memory kernels to handle 90% token sparsity in the KV cache.
It truly demands a full-stack paradigm shift. Every single layer of the stack, from the data curation protocols down to the low-level GPU silicon instructions, has to be unified around this native multimodal goal.
But, I want to leave you with a thought that goes a little bit beyond the CDA kernels and the loss functions. If we succeed in this architectural shift, if these early fusion models eventually process all sensory inputs, the discrete text, the high-fidelity audio, the high frame rate vision, inside a single unified mathematical embedding space with absolutely no distinct modality boundaries, will these AIs develop a synesthetic understanding of reality?
Oh, wow. That is a wild thought.
Right. Will they perceive the abstract concept of a loud noise and the visual representation of a bright flash in a beautifully blended native way that we as humans with our strictly biologically separated senses can't even begin to comprehend?
Because it's all just one language to them?
Exactly.
Yeah.
Will they literally see the shape of a sound because it all maps to the exact same geometric coordinates in their latent space? Something to think about while you're watching your next massive multimodal training run hopefully converge. We'll catch you next time on AI Paper Slop.